So we are now ready for the after-dinner program, which I'm really looking forward to. It will be hosted by Jim Peebles, of course, well known to all of you, but perhaps most important, former member of the Institute for Advanced Study. But of course also actually Albert Einstein, Professor Emeritus at Princeton University, a great series of achievements. Of course, with Bob Dicke, predicted the CMB, his work on clusters of galaxies, dark matter, and one of the first to resurrect the cosmological constant. Now, this dinner might be kind of dangerous. It reminds me of a kind of famous dinner at the Institute for Advanced Study in 1945, where he actually celebrated Wolfgang Pauli's Nobel Prize. That he couldn't travel to Stockholm, so the award was here. There were terrific speeches by Hermann Weyl and the art historian Erwin Panofsky, but then there was an impromptu speech by Albert Einstein that he didn't write down. And in that speech, he crowned Pauli as his successor. Of course, there were very few witnesses, and there was nothing put on paper. So I just want to make sure that the younger physicists here are ready to be crowned, possibly. But I think more important, we will be spending time with some wonderful people here and also kind of celebrating the legacy of two great Princeton physicists that have been here on the podium already for some time, John Wheeler and Bob Dicke, and love to give the word to you, Jim, to lead us through this program.
Robert, thank you for that nice introduction. Wonderful to take part in this joyous celebration. Why don't you guys come up? We have organized Charlie and the rest, recollections of a time when there was a great transition from research in general relativity theory that in the early 1950s was, in Freeman's terms, in eclipse. Very little research done, and on the experimental side, it was close to zero. It was perceived that about all you could do that is meaningful to make marginal additions to the classical tests. A decade later, in the early 60s, the situation was very different. A vibrant research activity was going on. The first slide shows the two leaders you have just seen, John Archibald Wheeler. He is third from the right, then two over, Robert Henry Dicke. A photograph taken at about the time the two of them decided that general relativity theory and gravitation are too interesting to receive so little attention. They were in their early 40s at about this time. They had already had illustrious careers, John in nuclear physics and particle physics, Bob in what we might call quantum optics. They had decided, though, independently, I think, but at very nearly the same time, to found research groups in gravitation and general relativity. I date this renaissance of activity to the conference in the next slide at Chapel Hill in January of 1957. Can we get the next slide? Or perhaps I have to do it. We do. Whoops. Yeah, there it is. I will have to read it for you. It is important that you see some of these things. It is entitled Conference on the Role of Gravitation in Physics, which could be read to say, is there a role for gravitation in physics? I am fascinated to notice and draw your attention to the source of funding. You see some of the usual suspects, which I will, in order not to keep moving my head, I will read from a copy I made of this. Usual suspects: International Union of Pure and Applied Physics, UNESCO, United States National Science Foundation. But then you read further down, you read Wright Air Force Development Center, U.S. Air Force. And below that, Office of Naval Research, U.S. Army. You must remember that at this time, it was not long after the Second World War. military and big industry were deeply impressed by the contributions of physics in that war, radar, nuclear weapons. If those physicists came up with something new again, these people wanted to be in on the action. I never thought that was such a bad arrangement. For years, I was supported by the Office of Naval Research. Totally useless, but of course, the money that came to me was rounding error for the budget of the US Navy. I never saw anything wrong with that. But now, we look below, on the next slide. John, I marked this conference as the Renaissance, the onset of the Renaissance, because the lead two papers at this conference were by John Wheeler and Bob Dicke. Here is the title and an illustration from John Wheeler's paper, The Present Position of Classical Relativity Theory. That conference, the theory was split into two parts, classical and quantum. The quantum part as perplexing then as it is now. On the classical side, John Wheeler emphasized that a little imagination might make that subject more interesting. In particular, he said, imagine you have two Schwarzschild solutions, but imagine you take the throats and patch them together to make a wormhole in space-time, thread that wormhole with electric field, and what do you have? Charge without charge. He also described a geon, mass without mass, a nonlinear coupled gravitational wave and electromagnetic wave. On Bob Dicke's paper, The Experimental Basis of Einstein's Theory. Bob Dicke was an absolutely marvelous physicist, a lovely person, but he did not write gracefully. Consider his opening sentence. It is unfortunate to note. What a way to begin this. His point, of course, was very good. The experimental basis for general relativity theory then, in the late 1950s, was no better than it was perhaps in 1920. And consider the stark contrast to the tests of quantum physics, which he says are literally in the thousands. He set out to found a group and to remedy that situation. We are fortunate to have here representatives of both sides, John's side and Dicke's side. Maybe I'll not introduce you collectively, but instead calling you in turn. At that Chapel Hill conference, Charlie Misner, you were there, you contributed. Would you care to say a few remarks about what you recollect about that time in your life?
Thank you very much. I guess I have control of this. Yes, so I'm trying to think of what was happening then. I can't say much in just a few minutes, but I will try to say a few things. Now, first it begins before Jim's marked date, 57, because in a few years earlier, John Wheeler had accumulated a bunch of people working with him, and he took a few of us to Leiden, Holland, to work with him on general relativity, while he had a separate office in the Lorentz Institute where he did nuclear physics. And in the relativity office, there was myself, Joe Weber, worrying about gravitational waves. I was worrying about things related to wormholes and whatnot. Peter Putnam is not on the schedule of most people, but I think someone's trying to write a biography of him. He was a very extraordinary student that John brought back from his work in the Route 128 pre-Silicon Valley uproar. And he had taken all his raises in stock and apparently accumulated some and was able to help the university acquire several dozen very large-scale sculptures that are scattered around the campus. So, but then I also had as a room, Tullio Reggi came there, got started on some relativity things, and Hugh Everett was being discussed by visits to Copenhagen on his work on quantum mechanics. other things, so I won't say much more about that Leiden experience, except that it was the beginning of a wonderful career for all of us. Undergraduates, as we came back from that, undergraduates played a big role because Wheeler was always very strong on students. He didn't want to do anything without having students because they asked the right questions and made him think things from a different point of view. And so that went off to some of us, and Dieter Brill and I each got involved with undergraduate students. I'm sure Dieter will mention his work with Hartle, and I'll say a little bit more about my work supervising an undergraduate, Becca Darf, from the math department. Dicke was overloaded with his work supervising experiments, so when he had a theoretical idea, which is now called the Brans-Dicke theory, he decided that Brans would be a good student to do it, but it would be nicer if I took the burden off of him and made sure that it was done correctly. And so he handed me Brans and the theory, that is the clues of what the theory ought to be, and said, get him through a PhD, which was very successfully done. Then a visitor to the university, David Finklestein, I'm going to talk more about him because he made what I consider the most major improvement on the understanding of black holes since Oppenheimer and Snyder, and I'll say more about that. And finally, there was this friend of mine, Sid Leavis, who's here, and he had this wonderful idea after having done experiments with Dicke on things that I didn't get involved with, but I was amused by, as he was, this idea of gravitational lensing. And he was so involved with that he produced a model of a gravitational lens. And I've been able to, he donated it to the University of Maryland because they can take care of such things. And I brought it along with me, and you can look at it. But if you look through that, it distorts things in exactly the same way that this is a black dot in the center would if it were a black hole. So I'm going to leave this around for people to look at. Put it on the table. And we'll say more about that. Okay. So here a few comments about what was going on in Leiden. And I think I don't have time to go in any great detail about any of these things. And then Dieter Brill will say something about his work with Hartle, I'm sure, which was very important. Now I mentioned Becca Darf, who was an undergraduate in the math department, and after Finkelstein's discovery of the black hole horizon, I had him do some work on that I'll say more about. There's what I told you about Brans being dumped on me to make sure he didn't make any mistakes developing the theory. And Finkelstein I do want to talk about because I think he's often overlooked in the story of black holes. Finkelstein published a paper which he described a perfect universal membrane at the distance r equals 2m in the Schwarzschild solution. Up until then, it had been often described as a Schwarzschild singularity. Some people had discovered there was nothing really singular except the coordinates, but no, and I think at least no one who made any impression on the physics community pointed out the fact that there was this tilting of light cones that made it possible for light to go only one way, depending on which solution you chose, either in or out of this horizon. So Finkelstein describes that work with me as a byproduct of a program with me, which was completed in a year later. But in a nice book that people gave speeches in my honor a few years ago, he describes his memories of that occasion as being a most exciting time. And I want to tell you what was going on where I gave him an important clue that he turned into this wonderful discovery. And so he came to my office because he had some ideas about the relationships between topology and spin. What's the difference between spin 1/2 and spin 1 in the way that the rotation group acts on them. And he wanted to see whether there's anything in gravity that would allow a similar phenomena. And so he wanted me to help him understand the topology of a metric being assigned to a space. And I had been working so much with mathematicians that I knew how to do that, and I explained it to him. And the question was, why did he have a hard time? Why did he have to do something new to visualize tumbling light cones? Well, I think it was because at that time, two technical things, contravariant versus covariant vectors, were regarded as just different ways of labeling the information in a vector field and not having any intrinsic difference. But that viewpoint fails completely with null vectors, because a null vector lies in the surface. The contravariant null vector lies in the surface that the covariant vector defines, and yet it's not yet considered orthogonal to it. So it's a really weird situation. And for null vectors, you've got, whoop, pushed the wrong button. Have to go back again. Maybe that will do it. You have to understand that you have to use contravariant vectors to make a picture of what the light cone is doing, if it's doing something. In the Minkowski space, it just fixed, it stands there. So I showed him how to do that, and he ran from there completely on his own without my suggestion or help in any way, and produced this paper. And he drew these pictures of light cones. That's what I taught him how to do, was how to draw pictures of light cones. And as the text says, I'm curious whether anyone ever drew pictures of moving light cones before this. I haven't had the time to study the literature and find out, but I'd be curious to know whether such pictures had ever been drawn before where light cones are moving around. Anyway, that was the clue, because you see in here, whoop, I do have a pointer if it works.
What year did you say that was?
That was 58. So here, well, no, this doesn't work very well. Here.
Use the gadget that you
Okay.
advancing slide.
Use your arm.
Yeah, use my arm. Well, then I need to carry a microphone with me. Yeah, if I use my arm, you can see the light cones are moving around, and on this surface, light can only go out, it can't come in, if it's within the light cone and moving forward in time. And of course, you could do the whole thing backwards. And he had no interest in astrophysics, so he didn't relate this to anything going on in the real world. It was just some picture to help him worry about what amusing kind of things Einstein's equations allowed. So now we'll go on, and so I had Beckenstein do an upgrade of the Oppenheimer-Schneider collapse, which I believe is the first time that the collapsing empty space-time outside the collapsing matter was ever displayed in the solution of a black hole. And I think that's important because it's only the empty space outside that's still available to us. All the matter has been thrown out of the universe a long time ago when a black hole was formed, and we're only left with the curved space inside the black hole that could only be seen with Finklestein's viewpoint, and a mild improvement due to Kruskal, which was published after Wheeler learned about Einstein from Finklestein from me. He said, oh, I've heard something like that from Kruskal, and Kruskal wasn't available to write up the things he discussed with Wheeler, so Wheeler wrote a paper under Kruskal's name, and it was published. Kruskal never saw anything about it until the proofs came, and Wheeler wouldn't let him change the title. So it was published under Kruskal's name, but there was not one period in the whole thing that was contributed by anybody but Wheeler, interpreting Kruskal's ideas from a napkin on a lunch hour some previous year. Anyway, that's more convenient computationally, but it doesn't have the insight of the existence of the horizon that was first discovered, in my view, by Finklestein. So that was a great thing happening here in Princeton as I helped him get the tools to be able to discover the essential features of a black hole. There are some things I don't have time to show to you. That's Bekenstein's view, where one sees, as Oppenheimer-Schneider, collapsing matter. Then Oppenheimer had a section of the Friedman universe, but what was new was in these Kruskal coordinates, motivated by Kruskal's insight, that you can look at empty space up here and things are going on there. And if you look, that is a very important view of what's going on in the world. Okay, there I've got something, but not time to talk about it. And now I want to turn this whole idea over to Sid Lewis. He not only invented, not knowing that Einstein did it earlier, gravitational lensing, but even Sid may not realize how much this is being used these days. As you see in this iconic picture of what I say is taken by the dark matter telescope, because in this picture, you see these blue blurbs. These are dark matter that have no interaction whatsoever with light. And we see them because the Hubble telescope has looked through here and got nearly 1 million galaxies in the far distance. And those galaxies their images are being distorted in such a way that you can deduce the gravitational fields that are causing those distortions. And from that, deduce how much matter had to be there that's not visible optically. So that's a great device entirely based on gravitational lensing. And so here, if I don't know whether I can click this, I think it doesn't work without the computer to get that, to show that next picture. But, and then I'll skip the rest. I don't think I have control of the computer, so I can't show you the picture of what you see through this lens over here as time proceeds, a star passes past the black hole. So sorry I can't do much more.
Thank you, Charlie.
It took too much time.
So another student of John Wheeler at the Chapel Hill conference was Dieter Brill. Dieter, would you care to say a few words?
Now, how do I?
Gracefully moving.
When I came to Princeton in 1955, it was a wonderful thing to be a student of physics, because there were all sorts of great things happening in all fields of physics, most interesting and wonderful, and particularly also, at least in theory, they were fundable. There was never any problem that you had to worry about what you're going to do after you get your PhD. The assumption was physics was considered sufficiently important that you would find a way to continue. And so one could just choose what was interesting. And the other thing that was great was the fascinating faculty that we had at Princeton. And in particular, the people that influenced me was, in the beginning, John Kemeny. That was when I was an undergraduate at physics. And he was teaching a course in the philosophy of science and mentioned general relativity as one of the topics that was interesting also for the philosophers. And I sort of made a mental note that I have to find out about these things, but there was really no way to do that while I was an undergraduate. But then when I came as a graduate student, there was Bergman, who was giving a course where he built a magnificent edifice of general relativity as a very nice and ordered and, in a way, complete system. Later on, I met John Wheeler, who had this vision of how to get more out of and draw more wonderful thoughts out of this edifice. And there was Dicke, of course, who was an enormously clever and practical person, applying his talents to general relativity questions. And he was the one that gave me a TA. So for a while, I was working for Dicke. And here's a picture of Dicke and Bargmann at that early time. I don't have any pictures of Wheeler, but I guess everybody knows what John Wheeler looks like. I started working on what was, well, it was the Edwards experiment. It was called the ill-tempered gravichord. And I was just doing one very small part of this important experiment. And I was working a lot with Bob Kropkoff. There's a picture of Bob Kropkoff, who was also sort of the theoretician of the group of Dicke. I learned a lot of important principles in general and in particular about experimental physics. Just the meaning of free fall. What does it mean that the Earth is really in free fall about the sun? I learned about various methods to do precise experiments, the importance of null experiments, that those could really tell you about important questions. The feedback, the idea that you use the feedback system to measure things rather than the pointer reading, as it were, instead use the feedback that you use to make the pointer come back to zero. The synchronous detection of signals. And later on, although I didn't really continue with Dicke, I was still following his work. I was very interested in what he had to think about Mach's principle and the various ways that he thought of modifying the theory of gravity in order to see whether maybe nature did deviate from Einstein or not. In order to get an idea what you ought to measure, you have to know how things might fail and how big the results might be. So he engaged in this theory that was later known as Brans-Dicke theory, and I continued my interest in that. And in fact, I later had contact with Pascal Jordan and had the chance to tell him about Dicke's ideas. And well, he did need telling about Dicke's ideas because it was only Dicke that straightened out how to really interpret these theories. And finally, it in a sense culminated in Dicke coming around one day and saying, "Boys, you're going to write an article in this book that summarizes the present knowledge of gravity." It was written by Lou Witten, the famous the father of the somewhat more famous Witten these days. And so Kropkoff and I and Bertotti wrote this article, which was a great way to review everything that was known about experimental physics. But for my thesis, I decided to go with John Wheeler, who was so inspiring and had these visions. Here's a picture of that time of Dicke and myself in Verona at a summer school. Wheeler had, in a way, the opposite idea of Dicke. He said, let's not change the theory, let's just see, let's really follow out what we can get from the way the Einstein theory is. He had this famous way of phrasing his questions in a very picturesque way. So is space-time just the arena, or is it really everything? Is there some way to get all of physics out of Einstein's theory, basically out of space-time? Something that he called daring conservatism. Don't change things, but dare to make, to really get to all the conclusions that you can get. So that led to various sort of models to demonstrate that indeed these things are possible. For example, to get something that has the properties of a mass out of general relativity without putting in anything that is a mass. Mass without mass, and similarly charge without charge, and there was a whole program of getting that kind of thing. Well, as a problem in a course that Wheeler was teaching, he was giving this question whether you can do the same thing out of spin. He had previously found the geon, which was this mass without mass, an entity that was just made out of electromagnetism, electric waves that are bent into circles and in a compact form, and they had some energy, and it was mass, and it acted like a body with some mass. And the question was, can you do that with neutrinos? So I went ahead and found out how one describes neutrinos in a gravitational field, which I thought was not so obvious, but it turned out that actually there was a 1932 paper of Bargmann that had solved all that. Anyway, so we repeated that, and actually when we then wrote the paper, with the enthusiasm that Wheeler always had, it attracted much more interest than the original Bargmann paper did, but it was based on that. And we managed to make a geon, and then came the time for my thesis, and that was a different question. It was the question about gravitational waves. And at that time, nobody really knew whether gravitational waves were real or whether they were just some artifacts of a theory. And Wheeler said, well, if you can show that gravitational waves actually have a mass, then there's certainly something real. And the way to show that something has a mass, a conserved quantity, is to look at things that have to be true at all times, namely something that comes out of the problems, out of the equations that you have to satisfy at each time, not something that has to do with the time development of what happens to space-time, but initially, what are the conditions that you have to satisfy there? So the initial value problem, and I managed to do that for a rather special case. Just for the axially symmetric situation, I managed to show that there are gravitational waves with positive energy. It is somewhat ironic that the general theorem then for all kinds of gravitational waves independent of symmetry was shown later by the other Witten, Ed Witten, and he used the very idea of spinor fields, the things that I had used before to generate the neutrino geon, but I didn't make that connection. I feel kind of humble about that, but that's how it should have been done. I had all the individual pieces, but I didn't put them together. Anyway, I got my thesis, and here are some pictures of some people that were around at that time, of all groups. sort of interesting. We had at the graduate college the possibility of inviting various professors for dinner and talk afterwards. And it so happened that we invited Eugene Wigner. This actually was in my room at the graduate college, and there are various people that are conceivably recognizable. For example, Bill Hoffman there at the left, and Frederick Werner next to him, of course, Eugene Wigner here, and this one here is Richard Lindquist, and he is also in the view to the right, Richard Lindquist, and various other people that some of you might recognize, but this fellow over here is Steve Weinberg. So it was a distinguished group. Dick Lindquist in particular was one that I collaborated with, and I guess I'm not quite there yet. He did a number of things that I think were quite important in various areas. He constructed these so-called lattice universes. There was the Boyer-Lindquist coordinates of what is called the Kerr solution. And in particular, he had a very simple, which I collaborated with him, but interesting solution of this infinite initial value problem that later turned out to be important for numerical calculations, to check and see whether the I'm running late. Okay. So that was Lindquist. I wanted to mention undergraduates. I guess I'll skip that. There were a number of undergraduates that also did contributions, and the only, why doesn't this go on? Well, I was going to tell about, this is, by the way, Jim Hartle at an early stage, and an interesting experiment was done there, and the rest of it was just some parties that we used to have with Dicke, and here's some early pictures of that.
We've made an executive decision that pardon me, all but Bill Hoffman may move down where they can see the slides. Feel free. At the Chapel Hill conference, the moderator for the discussion after Bob Dickey's paper was Peter Bergman. He began, can you say something about those experiments which it is rumored are going on at Princeton? He mentioned 3 experiments. The first, a pendulum experiment by Bill Hoffman, who will share us memories of what he was doing back then.
When Jim asked me to join this panel, I looked into my very disorganized collection of slides, of Kodachrome slides, and I found several going back to 1965 or 60, or 55 to 60, and I thought I would use those to try to give an impression of what it was like to be in Dicke's group in those years. The first few are locations or buildings. And what do I do here? Yes. Einstein's house on Mercer Street. This was certainly very important to all of us. However, Einstein died in 1955, the same year that Dicke came back from his sabbatical at Harvard and started his experimental program. So most of us never had a chance to see Einstein walking on the street. John Wheeler's house to graduate students, John Wheeler was the key person to bring general relativity into contemporary physics activity, theoretical. But to many of us, the most important place was Robert Dicke's house near the Firestone Library on Jefferson Road. It was there that Annie Dicke made picnics and dinners for graduate student gatherings with Dicke. And he lived there with Annie and his 3 children. Ah, sorry. Please keep me in tabs here. That's the house of Dicke. He later moved, but that was the house we knew. And then the graduate students were important too. So I'll show you one of the places in a small apartment in Charlie LaPlaca's apartment house. 3 physics graduate students crowded into a small apartment. And at different times, 2 of them were Dicke students and 2 were Wheeler students. So it was a familiar place for us. One of my favorite buildings was Palmer Physical Lab, and watched over by Joseph Henry as we came and went day and night. Interestingly enough, you might not believe it, but at that time, graduate students were free to park in front of the building. I showed Bob Dicke's office upstairs. When I arrived in Princeton, I was surprised to discover that Bob Dicke shared an office with Don Hamilton, who later became dean of the graduate school. So that's the way they were then. It was in that office that every week the students and associates of Dicke met for discussions. And usually one person or 2 presented the work that they were doing, and the rest of us tried to understand it, and also they presented their problems, and we tried to help solve them. And that was really exciting because there were so many things to learn, and there were so many different techniques of these experiments that Dicke had suggested. Oops. Now I shut it off. Okay. There. My favorite picture, Bob Dicke. He was always spirited, generous, friendly, and I never knew him to get angry at anything or anybody. He was full of ideas. It was his enthusiasm and imagination and creativity that attracted so much of us to go into experiments so far from the mainstream of nuclear physics, atomic physics, and elementary particle physics that most students went into for looking forward to their careers. I don't know whether we were daring, smart, or foolhardy, but anyway, it was a great trip. Now I'll show some pictures of the students. Carroll Alley, one of the senior students, he worked in gravitational redshift. At the time, he lived in a house with his wife and 2 children right next door to Robert Cassidy-Sue, who was a concert pianist. And Carroll loved to tell about how in warm weather, when the windows were open, he had his private concert, his private piano concert when Cassidy-Sue was practicing. Carroll went on from Princeton to the University of Maryland, where he continued in gravitation and atomic physics. Ken Turner, very different kind of experiment, this time trying to determine whether clocks varied with motion relative to distant matter using the Mossbauer effect. Ken then went on to the Carnegie Institution for Terrestrial Magnetism in Washington, and then became director of a radio astronomy observatory in Argentina. Jim Fowler, who's one of my associates here today, Jim did a G measurement, gravitational constant measurement, with a falling body. And this was something that Dicke was extremely interested in, the possibility that G, capital G, was not a constant, but varied. Varied either because of motion relative to distant matter or varied secular way. And he suggested several experiments. One was the one that Jim did, another the one that I did. Jason Morgan did another G variation experiment. This time, the idea was to study earthquake occurrences to see if there was a pattern of earthquake occurrences related to the Earth's orbit around the sun, hence due to gravity being affected by motion to distant matter. A pretty daring experiment, but Jason did a good job, and then he had a career in the geology department at Princeton. Well, you certainly recognize this person. We all looked much younger then. What I did was G variation with a pendulum. Dicke's idea was if you make a very small pendulum and you operate it as a double pendulum, basically upside down, it can be at a high frequency, namely, in this case, 22 hertz, and get around disturbances at low frequencies. And this experiment I did, and you might notice, however, on my desk, well, it's hard for you at the distance to see, but I'll tell you, on the desk was a slide rule. We didn't have PCs at that time. So the experiment was a little pendulum. This is 1 inch high, fused silica with a bob at the bottom and a narrow stem supported by a quartz fiber. And it actually rocked at 22 hertz, and the bottom was a flat to use with optical light to monitor its motion and measure as well as possible the frequency in order to monitor G over the period of a year, and to put a lot of effort, as you can imagine, in trying to reduce noise. We heard a lot about LIGO and all the effort to reduce effective vibrations and seismic things and noise. Well, this was the same problem, but it was a much more modest budget. Well, we used whatever techniques we could, and again, from a distance, I'll just have to tell you, but the method of measuring the frequency of this little pendulum was to phase lock a crystal oscillator to it. Kind of surprising to do it, but with a variable capacitor tuned by motors, and these are, on this slide, two hobbyist Aristo-Rev motors, one used as a motor and one as a tachometer, put together to keep the crystal oscillator following the pendulum. Wow. And the I'm not sure what comes next, but I'll tell you what I did next. The data I acquired over the night, generally at night. I took a air mattress and a sleeping bag and went out on the lawn behind Palmer Lab and would get up every few hours and look at the data and record something and readjust it, and did that over a good part of a year, actually. It was quite a tedious effort. And then used Fourier transform to see if it had any annual variation to it. Well, that was before the fast Fourier transform. Jim Cooley and John Tukey published that in 1965, and this was 1960. It was also really just a few years after Fortran was developed, which was published in 1957. So it was a very different era, and for doing the Fourier transform, I was given the key to the computer lab, the Princeton University Computer Lab, and went there for the night, all alone, with a pile of punched IBM cards that Bob Krotkoff had coded for Fourier transform, and ran the program, and through the night and in the morning came up with the results, which were that G variation annual was at the upper limit was 4 parts in 10 to the 8th, which was, to me, quite impressive, but it was a little bit worse than what would have been really interesting for possible alternative relativity theories, such as the scalar theory, which would have come in maybe around 1 times 10 to the 8th. Well, almost 25 years later, 4 of us who had gravitated to Tucson met together with Dicke when he visited Tucson. And this is a photograph of the group. And Henry, from the left to right, Henry Hill, who worked on the solar oblateness experiment, and later went to Wesleyan and then Tucson, University of Arizona. Bob Dicke, Jim Brault, he measured the redshift of spectral lines from the sun by building a very specialized spectrometer, and later went to Kitt Peak and built the spectrometer for the solar telescope, which became the workhorse of that telescope. In fact, it was so successful that it was used in nighttime star work too. And John Stoner, who looked for variation in the fine constant over the course of a year. In the back row, myself, my wife Zilka, Louise Hill, Annie Dicke, very sweet woman, and Marby Brault. So this is the crew. The last slide I won't ask you to read at all, but it does show a list that I put together. It turns out that there were 24 people who worked with Dicke during those 10 years, and 17 of them were his students. Quite impressive. Thank you.
Thank you, Bill. So, what of those is my notes? I've forgotten what I do next. Oh, here it is. Good. So, also at Chapel Hill, Bob mentioned an experiment to check the acceleration of gravity and its dependence on the nature of the material. You know, of course, that Einstein built his theory on the notion that inertial motion is the apparent gravitation is simply inertial motion, and so it ought to be the same acceleration independent of the material for a test particle. The celebrated experiment showing that in early days, back at the turn of the century, the beginning of the 20th century, was by Baron Roland von Utwisch. He did a heroic job, but Bob saw you could do it so much better with modern equipment. He was responsible for, directly and indirectly, 2 experiments at Princeton doing this. Sid Levis was working on one of them, which I remember hearing about in early days. I remember also him showing us this gravitational lens as he became interested in that subject. I hope Sid is still with us. I don't. Sid's over here. Ah, good. Would you come join us? No problem. This is an uneaten salad.
As Freeman Dyson walked toward this podium, I said, uh-oh, I have a chance of finally doing something at least as well as he does. He leapt onto the podium, and I preferred the stairs, so I haven't won yet. I'm the Rip Van Winkle member of this team. The last time I attended a physics conference was half a century ago. I haven't done physics for 50 years. And I want to thank my friends and colleagues for digging me up and resuscitating me and bringing me here a week before the conference. So my last contribution to physics was in 1957. This particular slide, I don't remember creating, but I got it from Jim Peebles. He thought it was Dicke's version of the repetition of the Eötvös experiment, the famous do the feather in the rock fall with the same acceleration experiment. Actually, that's a picture of the device that I built. I was invited by Bob to go to Princeton after I got my PhD at Stanford. I had been looking for a place to do gravity research, and George Pake said, Dicke. So I called Dicke. He says, come on back here, be an instructor, and start working with us. So I got back there, and he suggested a version of the experiment that was different from the one he was already working on. I hadn't planned to discuss this. I was going to skip the slide, and I will because time is short. But basically, I will tell you we got a 10 to the 10th null result on a pendulum that was supposed to be sensitive to the daily motion of the sun. So in the morning, the pendulum was going to move more rapidly than in the evening if there were a difference in the gravitational acceleration, in this case of platinum and aluminum. So it was a 10 to the 10th null experiment on the frequency. I will also tell you that after I finished construction of this extremely delicate device, which was constructed of fibers a mil in diameter, and a pendulum at the bottom, which is basically a horizontal pencil stub with the stuff at opposite ends, I would wind it up in its vacuum, and it had a period of 10 minutes. I would, every 3 months or so, have to have it a little bit more amplitude. We monitored for a couple of years, and we could see no effect up to 10 to the 10th in the frequency. So toward the end of that experiment, before I had a chance to write it up, several oscillations of my subconscious clicked together, two numbers that I knew. One was the angle subtended by the average visible star in the universe at about 1,000 light years away. That angle is the size of a grain of sand, not a grain of sand, a thousandth of an inch diameter particle hovering over New York City viewed from this podium. And so you guys who are working on stars and galaxies are working with nothing. Little tiny things from the view of the Earth. So at any event, I knew the 10 to the minus 11th number. And I don't think many physicists perhaps did, but I'll tell you practically every physicist knew that light bent in passing by the sun through an angle 1 million times greater than the angle subtended by these stars, and therefore my subconscious said to me one day, "Pow! Stars cannot eclipse one another. Randomly paired stars in this universe will create a ring of light around the intervening star." And I ran to my desk to compute the size of the ring, and the ring turned out to be, for typical stars, like one at maybe just a little under 1,000 light years, one a little over, the ring just turned out to be 1,000 times the size of the star that was being imaged. I then realized immediately, knowing one more number, that to resolve with an earthbound telescope, you cannot look at something smaller than 10 to the minus 5 radians. This was 1,000 times too small to see. So I pushed it to the back of the desk for 1 year. And then two critically important observations, that without which I would never have done this thought that I'm going to put to you. The building, the Palmer Physical Lab, which Bill Hoffman showed a little earlier, had an exterior of multicolored bricks. Had not had those multicolored bricks, I would not be standing here. Furthermore, my office was a large office I shared with Val Fitch. When I paced in that office, when he wasn't, there were very small window panels that were terribly warped. It was an ancient building. So guess what? One day I'm walking back and forth, pacing, thinking, what am I going to do next? And I see this little white brick get big and small and distorted in all kinds of shapes, but every interior patch of the brick seemed to give my light as much light as every other. I said, I never computed the thickness of the ring. So I ran back to the desk. I compute the thickness of the ring. It's the radius of the star that's imaged, and therefore, in a perfect alignment, you get 1,000 times as much light. That becomes an observable. Now, that's the extreme case. 1,000, a little more if it's perfect. Those are very rare. These events are very far apart. So I think I'm going to close with the remainder of my slides. This is just think of an indication from that paper I wrote following, an star, what I called a deflector star, and an eyeball, some kind of a sensor. The light can go around in two directions, and the next image shows one star. This is the deflecting star. This is the source star for the light. When it's getting closer and closer to the deflector, this image here, number one, lags behind, and a new one appears over here to the right. It's small, and that's large, and the total of the two is somewhat more than the area of this in terms of the solid angle. So the light is increasing from the sum of the two until it gets into two bananas that ultimately merge into a perfect circle. This perfect circle is completely out of scale. In reality, for the one I described to you, the diameter of the circle would be roughly 1,000 times the diameter of that little circle on the inside. This I'm not going to dwell on. It happens to be my schematic of what the galaxy might look like from the outside, and how I was going to make computations for frequencies of occurrences, events of different amplitude and the characteristic shapes. I took a quick look in the literature before I came. There are people using this. Some of you know much more than I do about how gravitational lensing has been used. This is all only stellar gravitational lensing, but for discovery of exoplanets, planets circling around the intervening star will disrupt the ideal shape of the curve. Stellar astrophysics, evidently you can study atmospheres, stellar masses, and binarity, and then conduct senses even of objects that are not visible to the human eye. Thank you.
Thank you, Sid. Also at the Chapel Hill Conference, Bob mentioned the hope that perhaps one could track the motion of the moon around the Earth, because he was very taken with the thought expressed by Dirac that the strength of the gravitational interaction is wonderfully weak compared to that of electromagnetism, and he suggested that's because the strength of gravitation has been decreasing for a long time. He was very taken with that notion. He asked himself, could you detect an evolution in the strength of gravitation? His urging of people to think about how you would measure the distance to an object, ultimately the moon, has led to spectacularly tight tests of general relativity. And Jim, you were in on that action. Would you care to have a few remarks?
Okay, thank you very much. Can you hear me without the microphone? Yep. In the back? Good. That's great. So my talk is slightly different than the one you've heard so far. This is for this. So I would tell you, why did I come to Princeton in the first place? I came because I was an undergraduate in Indiana. 2 Princeton PhDs, Milo Sampson, Ken Ford, were at Indiana. One day I was working in a laboratory, and Milo Sampson was sitting on a table watching me. He says, Jim, where are you going to go to graduate school? And I said, I don't know. He says, why don't you go to Princeton? I said, where's that? And he said immediately, that's where Einstein's at. So I did go there, actually. I arrived 2 months after he had died, unfortunately. And so the kinds of things that were going on that I remember, this colloquium, Miss Wu talked about parity violation. Joe Weber, who was spending a year at the Institute here, came to Princeton and gave this first talk, I think, that he ever gave on the possibility of detecting gravity waves. It was a very exciting talk to be at. R.V. Jones, well, Reg, I learned to know very well. He was paid by the NSF to go around and talk at various universities about how you design apparatus. He was Churchill's right-hand man, actually scientist during the Second World War. He wrote the little book, not so little, Most Secret War.
One paper you saw there with a long list of authors, it must have been 20.
Yeah.
I remember that Bob often lectured to us on the hazards of big groups and of the dangers of sharing data which may be analyzed in stupid ways. I remember that when Ed Groth was considering joining Space Telescope, Bob said, don't do it. You'll be locked into programs that you can't control. I notice also that, that Bob dropped off laser ranging at about the time the number of authors grew to that length. It was just not his style. And of course, it's still true.
He was on the first paper.
Yes, he was. And in fact, he was on papers, many leading up to the lunar laser ranging. But he had a very good point. Big data is with us. It's deeply important. But it's awfully hard in big data to find what you don't know to look for. And that, of course, was what Bob always loved to do. Look for the unexpected.
Can this miserable experimentalist just say 2 minutes?
Of course.
Because it's, you opened the door to an interesting story. I don't need that.
No.
Galileo filled his lecture room, I'm told, with his voice. He didn't have microphones. So at the time, we had the data coming in. It's very hard to analyze. So the people at Jeffrey Paulson Lab who do ephemerides and do things like that were doing the analysis, Jim Williams in particular. And that was, they were part of this lower team group. But Erwin Shapiro at MIT wrote me, I was the chair at the time of the group, and I said, yes, you can have our data, please have it, and help us, just do it, just let us know how it's going. The JPL people made a mistake. They had a wee term over here that they thought was quite small, and it was small, but the problem was, underneath it was the denominator that was even smaller. So they threw it out. And the net result is the initial results obtained by the Lure team, which would have been a smaller group of physicists, disagreed with Einstein. And so Einstein, we felt, was be absolutely sure that it would fall at the same rate. Otherwise, it's not geometry. So what to do? We waited. We waited, and then they checked again. They looked again. They couldn't find anything wrong, so we were on the verge, 6 months later, of publishing a profound result that Einstein is wrong. General relativity has a flaw. In the meantime, Erwin Shapiro caught up and he said, hold it, we've analyzed your data by King, Shapiro, and I can't remember the third one now. Probably Reason. No, it wasn't reasonable. Anyway, and we find no problems. So tell the JPL people, oh, better analyze it again. So they went very carefully. They kept these small terms that they threw away. One of the small terms was actually very important. And it made the 2 experiments agree. And then the next week was published in Fisher and Blatters back to back. So I think in this case, having an independent group of really good people, it was King, Councilman, and Erwin, saved the day. Okay?
Ray Weiss, you came to visit Bob's group for 2 years. You built some things, a gravimeter, and you talked a lot to people, and perhaps you have some recollections.
Yep, well, they're right there. I'm not going to, let me get to the microphone. I can't do what Jim did. No. At any rate, let me move this. Yeah, I was a postdoc. I was not a student, so I'm in a different category. And the first thing I ran into was Jim Brault. And when I got to Princeton, and I'm not going to go through everything, but I had heard that the redshift in the sun had never really been measured, and it was true. And it turns out a very simple thing was done, and Jim, who I got to know pretty well, and here's Jim at later on in his life. I guess this is the middle button, and I guess we're out of it. Okay. That's Jim right there. And he's now, this is not the experiment, but this is on the eclipse expedition he was part of. But what they did is something very simple and beautiful. They used the modern techniques of spectroscopy, and you can see what they are. They wiggled a slit over a line that they got from the sun, so they were able to get a very precise way of finding the center point of the line, and they managed to see the redshift at the sun using the sodium D line, which did not partake in the general convection of the sun. So all of it was very, very smart. And I thought it was delightful to have joined a group that had such lovely things going on. The next thing was I didn't have much to do with the Dicke Etwash experiment, but there was a thing that came out of it which I want all of you to appreciate. And that's, none of these, this thing does work, but you can't see it.
doesn't reflect.
Ah, That's the trouble. There's no reflection. Okay, I got to take this. And that is the following, is here's that pendulum that you saw Jim show you. This is the two masses that are aluminum, and then there's gold right here. And this wonderful system to measure small angles using a wiggling wire telescope. And what all of this stuff does is it feeds back to this by some capacitance plates. And what it does is just what Sid Liebes said, was namely, you hold the position of that, you never let that thing rotate. You make a servo system out of it, and that does two things. And we use it dramatically at every other experiment that has been done using mechanical systems with very precision measurements. What you are able to do with this is if you have a quiet sensor, like that telescope, you can cool the system. You don't have to suffer the thermal noise of the system itself, which is profound. In other words, if you analyze that experiment, you find out it's a 300-degree K experiment, but the pendulum, that rotational pendulum, is operating at under a half a degree Kelvin. And it's a tremendous step forward in doing experimental work. And we use it in LIGO for everything. The thing I was particularly involved with was something which was a failure, which was a device which Bob was, what it was a device to look at the 0S0 mode of the Earth. That would be excited by scalar waves of the Brans-Dicke type, of the scalar type of the Brans, not the tensor type. And what we were looking for was indeed that the Earth would oscillate in a completely monopole fashion at 20 minutes, excuse me. And so we built, and a guy who worked with me was Barry Bloch. He was a theorist who loved to make things out of quartz. And this is the thing he made. He made a little gravimeter with a spring. And here are these capacitor plates to do the same thing as was done in the Etbush experiment. And we looked to see if we put this on in the same pit that the Etbush experiment was in, and we looked to see if the Earth did indeed shake at 20 minutes, and looked for excitations by scalar waves. It was a gravitational wave experiment using scalar waves as the excitation. You don't know much about this experiment because what happened was, while we were doing the experiment, there was this enormous earthquake, a 9.5 Richter earthquake in Alaska, and it set the Earth singing for the rest of the time that I was at Princeton. Okay. The Earth, and it has a very high Q. Here's the thing I'm going to dwell on, and this is my only other slide, but I really want to tell a story about Bob, which is most remarkable. Here is Bob and Mark Goldenberg, and with this experiment was the solar oblateness experiment. And what the idea was is to look how round was the sun. Now, why did Bob want that? Because, you see, if the sun was somewhat oblate, he would get a somewhat backwards perihelion advance from the sun, and then he had more room for the scalar field, turns out. So he wanted to find out, it was a term that you should have been looking for anyway, is the sun oblate, making the gravitational term, that's a quadrupolar term that goes as 1 over r cubed, and causes the perihelion to go the wrong way. And so he set Mark Golden, this was one of these things that happened at one of those meetings that you engineered, Jim. He asked Mark, who had come from Harvard, who was a student of Norman Ramsey's, to find out what is known about how round the sun is. And what Mark found out is that the Vatican Observatory, one of the few people who did this, and the way they did it is they had a big cave somewhere north of Rome, and the people who were employed there, many of them priests, would take rulers and take a image of there was a hole in the top of the cave, and you looked at the bottom, there was a nice flat section of the cave, and you look at the image of the sun, and you measure with a meter stick the oblate and the prolate diameters. That's the way it was done, and that was all that was known, and the sun was not oblate any more than a part in 1,000. That was what these guys had measured. So Bob disappears for about something like 3 or 4 weeks. I can't remember exactly, but it was profound. He did not come to those Friday evening meetings, and I didn't know what happened to him. And all of a sudden, he comes in to the next meeting, and he has a sheath of blueprints under his arm, maybe the size of 6-inch of rolled up blueprints, and he throws them on the table, and he says to everybody who was at the meeting, build this. Okay? And it was this telescope. And Mark came to me with the drawings. And we sat together at my desk, and we leafed through the pictures that Bob Dicke had drawn, and we couldn't believe it. What was going on was unbelievable. I'll tell you why. You looked at, for example, the optical system. Here are the various things in the optical system. There were already not just one lens. There were lenses with certain sphericities, certain aberrations taken into account. He had done, he had made a system which had many, many optical components in it already. That was the beginning. Then you had a drawing of the whole telescope system itself, and all sorts of struts and pieces on it that none of us could quite understand. In other words, as you looked at each one of these blueprints, you began to realize there were things there that simply were beyond what you would have thought of right off. And then the electronic system, which is over here, of course, full of lock-in amplifiers. And that was a little, I understood that better, but that was, and so what came of that was most interesting. And this was a lesson for me and a lesson for all of us, but a really deep lesson for me. This was a work of a man who could do something that I couldn't do, and that is to sit in his chair at home and think through not just the concept of the experiment, but then the first iteration of the experiment as though you had already done it, and thinking through, saying, oh my God, this is not going to work because I have this particular small effect that I hadn't yet considered, and correcting for it on paper before you built it. Now imagine that. That's so completely contrary to the way all of us, well, maybe not everybody, but certainly me, does experiment. You build the thing in a sort of very conceptualized way first, it doesn't work right, and then you fix it. And but in order for this telescope to be built, what Mark had to do, in fact, and Henry Hill, who was also working with him at the time, what they did is they inverted it. They took all the fancy things off the blueprints and started building first because they didn't understand what all the other pieces were about. And later on, they found out they were needed. Okay? So that's a piece of, that's when I realized that Bob Dicke was a genius. Something completely different. I'd never run into another person like that. Well, thank you. Yeah.